Hi everyone, welcome to the part 2 of modeling flow through the porous media in Ansys Fluent. In the previous video, we generate the mesh for this catalyst converter, and here we'll go to set up our pressure-based flow simulation in Ansys Fluent. Here, as you know, this is the inlet flow, and the working flow is nitrogen gas, and the velocity inlet is 125 meter per second, and the temperature is 800 Kelvin. We have two porous zones in these two substrate here, and the data for this substrate is according to these tables, and we will go through these ones later. So just let me bring down this slide and then go to the Ansys Fluent. So I have my mesh file here. I just go and display the geometry here, and this is the inlet and this is the outlet part. First of all, I just check my Fluent unit is per meter, but I will go to the unit here under the domain and then change the length. It is something like this. You can click on one of this one, then type M on your keyboard. Click L, and then you will go to the length, and then you can just simply click on the millimeter and change your Fluent units here. So I've just changed this one to millimeter, and this one will automatically change. So I can close this window here. Next step is exactly here. Set up the solver, but I will keep the default setting here. This is a pressure based, and we are going to do a STD analysis, so I will keep this part in the solver part. Then I can go to the outline view also and go and check the setup here. I will go after general part, I will go to the model, and then I need to enable the energy equation. So I've just double click on energy and then check the energy equation. So it will be activate, and then I click OK to close the window here. Next part is the turbulence model, and this is in the viscose window. I've just double click and open the viscose model, and the default setting is the K omega and SSD, and I'm going to keep this model for this geometry and this problem here. So I will keep the K omega and SSD model for this problem, and so I will click on the OK. As I said, we don't need to do anything in the models here, so we just activate the energy equation and use the K omega SSD of turbulence model. So I will close the model and then go to material, and for the fluid, as we discussed, we are going to use the nitrogen as the working fluid, so we need to change this air to the nitrogen. So for the material, I will go to the physics, and in the material tab here I will click on the create or edit. So now I have this window open, so I need to select the nitrogen. I can click on the Fluent database, and the material type I'll keep this fluid, and then click here, press on the here and go down by scrolling down, go to the end part. So here I have the nitrogen for as a working fluid. So I can click on the nitrogen, then just simply copy, close this one. So now I have nitrogen here in this material list, and so I have add this nitrogen here. So I can close this window, but as you see, I have this material wrongly here. So I can just right click on it and use delete button to delete this material, because I don't need that one. I just need nitrogen as a working fluid. So next step is going to the cell zone condition, and in the fluid I have 5 fluid region. If you remember, so I have these 3 fluid here. I can show you, but I can just click on one surface here, right click and hide this selected surface. So I can show these 3. These 2 actually here, this one and this one, actually is our substrate and the porous zone, but these 3 our nitrogen and our working fluid here. So if I just display this one, you will see this one, and then next one I can go right click here on this fluid and then add to active window. So the end part is this one, and we have another nitrogen part between 2 substrate. So I will click add to active window, and now I can display the substrate and porous zone, the first one and this one, add to active window. Okay, so now we know these 2 will be our porous zone, and these 3 will be nitrogen. Okay, so just let me display again the whole geometry on the wall here. Go to isometric view. So first of all, the first fluid is this fluid 0. So I can right click and open the fluid 0 and then change the material from air to new material nitrogen, and then apply and close this one. The same will be repeated for this one. I can right click, edit, fluid 1, change air to nitrogen, apply, and then close. Again here, edit, change air to nitrogen, apply, and close. Next will be the first porous zone. So I will edit again this one, then again change the material to nitrogen. In this case, as we have the porous zone, and in our porous zone the fluid flow is laminar, so I will just select the porous zone. So this tab will be activated, and then click on the laminar zone. Okay, so I will go to this window. I can extend this part. So based on this data, we can fill out the porous data for the first porous zone. So first of all, we need to define our directions. Actually, we have 3 directions vector for 3D models here. but you just need to fill out two direction 1 and direction 2, and then Fluent will be automatically generate, and no, actually, the direction 3 vectors, so it will be automatically generated. So you just need to fill out and define the first two vector. But just let me explain you what is this two exactly is, this two direction. So if you look at this one, so I will keep first this default setting here. So it means that the direction 1 vector is in the x-axis. It means that it is, if you look at here, this is my x-axis, this side. So the first direction vector is x-axis. The second direction 2 vector is in the y direction, so here. And all these direction 1, 2, and 3 are perpendicular to each other. And so this is the y direction in this side. Now if we define these two vectors, Fluent knows the third vector, direction 3, is the z direction, and the z direction actually is the direction that the flow will go inside the domain here in this direction. And so we need to define the material in the porous zone and show the Fluent that the flow will be go only in this z direction. So what should we do? We need to put the viscous resistance for this direction, like 1e 0 power 0. So we need to put this viscous resistance in the z direction, and for the two other direction we need to high order, maybe like this one, to show the Fluent that the flow will not go through these two direction. So I only put 1e plus 3, and for these two I will take higher order like this one. So there is no way for the flow to go through in these two direction, and direction 1 and 2 are the x and y direction axis actually. So I will keep this one, and for inertial resistance I will set 1000 for all three directions. So I can apply, and then I can do the same for the next porous zone. So I will close this one, edit the second porous zone, and then first I will change the material to nitrogen, check the laminar zone and porous zone. This laminar, now it means that we have the turbulent flow in the inlet and outlet, and also in this region between these two porous zones. And for these porous zones, we only have the laminar area. Okay, so again, I will keep these two directions, x and y, and then again the same values for this one. I can copy, paste for here, and then apply and close. Okay, so that's it for the cell zone condition and for these 5 fluid zones. Then I need to go to the boundary condition. I have some walls, internal boundary condition, and inlet and outlet. For the inlet, I need to open this inlet. I can double click or right click. Then I can bring this up, and velocity is 125 meter per second. So in the velocity magnitude, I will put 125. And for the turbulence specification method, I will choose intensity and hydraulic diameter. And I will keep this turbulent intensity, but I will change this one to 50 millimeter. So this is the inlet diameter of here. We can simply check in space claim. If I go to the space claim and then go to the measure, select the measure, and then this is the inlet. I can just click on this edge, and you see the circle diameter is 50 millimeter, and this is the same for outlet. So I can just check here also. I will click here. You will see the circle diameter is 50 millimeters. So I will choose this one for the hydraulic diameter of inlet. The only values remain is the thermal, and this is 800. So I will put 800 Kelvin here. Then apply for this one, check again, and then close this one. And the next one will be the outlet. You can right click, edit the outlet, and then I will retain the default setting of 0 for gauge pressure here, but in the turbulence specification method, I will change this one to intensity and hydraulic diameter. I will keep this 5 for this backflow turbulent intensity, and again change this one to 50. Apply, and then in the thermal tab, I will change this one also, this backflow total temperature to 800 Kelvin. Apply and close. Now we need to specify the discretization schemes. So I will close this boundary condition. Then in the method, I can double click. Then I will switch to task page here. And then I can retain all the setting for this this problem here. Okay, so now I'm going to enable the plotting of the mass flow rate at the outlet. So I can do it in this report definition here. So I just right click on this report definition, new, and then surface report, and then select the mass flow rate here. So I will select this mass flow rate here. Then I will change this name to surface monitor 1, for example, and I will keep this mass flow rate here, and check mark this one, report file, report plot, and also print to console. And here I can just select the outlet. So then we can check the instability of the mass flow rate at the outlet during the iteration. So I will just click on the OK, and so it will be closed. Then I can go to initialization part, double click on this one. But in this case and for this problem, I will change the hybrid to standard. Then in this part, I will, in the compute from, I will select the inlet, and then I will keep and retain all the settings, default setting here. Now I can click on the initialize. So I will do it and wait for a few seconds for this initialization. And now it has been done. I just decrease the size of this window. Now I can save the file, the case file. So I will go to the file, write an case here, and then just keep this name, Catalyst Converter Case H5, and then click on OK and wait to save the file. And after that, we can start the calculation. Okay, so this part is also has been done. Now I can switch to the outline view and then to the run calculation here also. And then I can enter 150 for number of iterations here and then start to calculate. So I just change this one to 150 and then start to calculate. So I will click on this calculate and wait for the calculation. So you will see it has been started, and then as you see, this mass flow rate graph flattens out as you are seeing here, and also you have this scaled residual also. Since the mass flow rate has stabilized after 150 iterations, the solution can be set to have reached the convergence. So we will wait for a few maybe minutes and then check again. Okay, so the calculation has been completed, so I can click on OK, close, and then save the data file. I will just write on the case and data. I have the case, but I need to save the case and data file, so I just click OK. And this part is also has been done. So for the post-processing, I will create another video and then show how we can analyze this porous zone in this geometry here. So please go and watch the post-processing video in this series of video. Thanks for watching.